Okay, thank you. I'm presenting a joint work with Andrea Bracciali and Cristian Lepore from the University of Stirling, Alceste Scalas from the Technical University of Denmark, and Roberto Zunino from the University of Trento. The subject of study of this talk is Algorand. Algorand is a new generation permissioned blockchain, permissionless blockchain, which features a new consensus protocol, which is rather interesting because it is proof of stake, meaning that it does not consume a huge amount of energy like Bitcoin and Ethereum. And importantly, it guarantees the absence of forks. And this is important for smart contract because it simplifies reasoning about the correctness of this contract. Also, besides the consensus protocol, Algorand introduces a novel paradigm for smart contracts, featuring a rich mechanism of transactions which have features that we do not see in other blockchains, like, for instance, atomic groups of transactions or custom assets. And then it introduces stateless contracts and stateful contracts, so different kinds of contracts that suitably mixed together can be used to devise new kinds of applications. A problem is that all this complexity in the smart contract mechanism is not counterbalanced by formal definitions of the behavior of these features. So it's really hard to reason about the security of smart contracts in the absence of these precise definitions. So our contribution is a simple formal model of the transactions and of smart contracts in Algorand. And based upon this formal model, we are able to formalize and prove, some smart contracts and prove their security. The key of this talk is this message. Even using a formal model of Algorand, it is still complex to reason about the security of contracts, especially when they are not just toy examples, because there are many features that a smart contract developer has to take into account to understand if the contract is correct or not. And so the take-home message is that if one really wants to develop smart contracts in Algorand, one needs to create a new domain-specific language. And actually, there are already a couple of instances of these domain-specific languages that compile to Algorand, for instance, Rich and Clarity. And I've added this disclaimer to this slide. This talk represents the point of view of the authors about smart contracts on Algorand, and our point of view may substantially disagree with Algorand's point of view. So why do we want to introduce a formal model for Algorand? The starting point is that what we have learned from the history of smart contracts in permissionless blockchains is that bugs in smart contracts can cause direct losses of money. And a formal model can help to unambiguously define the behavior of transactions and of smart contracts, and at the same time can abstract from low-level details that undermine the understanding of smart contracts from developers. And further, a formal model can be the basis to devise new analysis and verification techniques that can eventually verify that the contract has no bugs. So overall, formal models are something that can help you to save money. These slides shows the evolution of smart contracts on Algorand. And after the launch of Algorand, they started to introduce a first layer of smart contracts, the so-called stateless contracts. As the name suggests, these contracts have no state. They are just like standard accounts that contain assets and can move assets upon transactions. Then, more or less 1 year after the introduction of stateless contracts, they introduced stateful contracts that are not a pure extension of the stateless, but are an integration. If you see in the figure, here I have a stateless contract together with a stateful one, and the idea is that the stateful contract does not hold any asset, but it refers to an external stateless contract, and a participant who want to interact with the contract, with the overall application, has to send an atomic group of transactions containing both a pay transaction, from which the participant can obtain money from the stateless contract, and an update transaction to update the state of the stateful contract. But then, after the introduction of stateful contracts, there have been further extensions. With TEAL version 3, they added new opcodes, and now they have announced AVM, which is a sort, I think, of Ethereum CVM, a bytecode language, which is Turing powerful. So I have no idea whether this evolution was planned as is from the beginning, or if it is caused by the other factors. But what we are done in this work is modeling the stateless layer of contracts, which anyway are fundamental also for the stateful case. So now in the following slides, I want to highlight some subtle features of Algorand to understand why all this richness and complexity eventually makes the reasoning about smart contracts difficult. So, but let me start with the easy features. Algorand is an account-based platform. This means that participants have wallets and they store assets within their wallets. For instance, here I'm depicting a wallet of Alice containing 5 algos, the native currency of Algorand. And here another participant, Bob, with 2 foo coins, where foo coin is a custom asset, which is native in Algorand, unlike in Ethereum, where you have to program tokens with ERC20, for instance. Transactions perform actions on accounts, and there are many, many different kinds of transactions. For instance, to transfer assets, to generate assets, to set asset managers, and so on. And the important point is that the actual behavior of transactions depends on many things, on the type of the transaction, on the transaction fields, and also on the state of the blockchain. The simplest case is depicted in this slide. Have 2 accounts, A and B, and the transaction pay with the sender B, receiver A, and I want to transfer 4 algos from B to A. So the behavior of this transaction is the expected one. Eventually, 4 algos are transferred from B to A. But this is the only easy case. The fields within transactions may affect the behavior. For instance, here I have the same pay transaction, but with a set close remainder to field. That says that I want still to transfer 4 algos from B to A, but I also want to close the account B and transfer the remaining amount of algos to another participant C. And so after this transaction, the new state is this one, where the account of B has disappeared and I've moved 1 algo to C. So the behavior of transactions may depend on fields within transactions, but may also depend on the state. For instance, here I have an apparently harmless transaction, a pay from B to A of 5 algos, but now this transaction fails. Why does it fail? It failed because I'm violating a constraint on the state, and in particular on the accounts. Here, the account of B has 2 kind of assets, the algo and the full coins, and so I have a lower bound of 200,000 of micro algos that I have to maintain within the balance of B. I cannot zero the balance of algos. Now what happens if I want to transfer not 1 algo, but 1 full coin from B to A? Intuitively, the behavior is just transfer this 1 full coin to A. But also this transaction fails. And it fails because participant A has not opted in to receive full coins. So this transaction requires a different state where A has opted in. And opt-in means create a binding in this map, which initially is set to 0 full coins. And after this preliminary step, the opt-in, I can eventually pay the full coin to A. But here I have other undesired and unexpected behavior. If B was set as the asset manager of full coins, what we can do is to steal the full coin of A. So A had 1 full coin, she did nothing, but B stole this full coin. So these are simple examples. It is perfectly appropriate that the transaction mechanism is rich. But then what happens when I have to program smart contracts? I have to take into account of these features. Another interesting feature is that I can group transactions in atomic groups and say, I want to perform atomically these 2 transactions. A pays to B 1 algo and B pays to A 1 full coin. And these 2 transactions cannot be fired independently, but the miner must ensure that they both occur in the same block. Besides these features, there are many other features. For instance, there are other constraints on accounts. There are transactions to generate assets, to freeze and unfreeze them. There are temporal constraints on when transactions can be appended to the blockchain. There is a very strange mechanism called transaction lease that allows to have mutual exclusion between transactions. And there are other features related to assets, like defining various kinds of assets managers, burn assets, delegate their management to other participants. Okay. Contracts, what they do is they authorize transactions. So since transactions have all this complexity inside, the smart contract developer must really take care of all the things that may happen. This slide introduces smart contracts in their stateless form. To understand them, it's easy if we start by recapping the normal transactions. Here, for instance, I have a payment transaction from A to B. And to authorize this transaction, as usual, as it happens in other platforms like Bitcoin, Ethereum, I need a signature of the sender, so a signature of A. And this signature authorizes this transaction. Stateless contracts are more or less the same. The difference is that the authorization is not given by a signature, but by a script that here I indicate as E, is a script. And the transaction is authorized, the pay transaction with sender E is authorized whenever the script evaluates to true. And here, besides the transaction, I can add further witnesses that can be used as arguments for the script. So the idea is to treat stateless contracts similarly to accounts, and indeed they're called contract accounts. There's something where anyone can transfer assets, but to transfer assets from a contract to some other participant, I need to run the script. Here I have a minimal example of a script written in the TEAL language. Here the desideratum of this contract is that I only want to accept transactions which transfer to B for algos. Nothing else might happen. So this is the script. It is more or less intuitive. The script says that it accepts only transactions of type A, and where the amount is less than 5, and where the receiver is the address of B. So I'm checking these 3 conditions here. And as you may imagine, if I try to transfer to B more than the 5 algos, the transaction fails because the script evaluates to false. And also, if I try to pay to another participant different from B, for instance, C, the transaction fails because this check fails. But now from the script, it may seem that this contract is secure with respect to the intuitive specification that I given before. Well, this is not true because the contract accepts a transaction of this form, a transfer where I transfer 0 algos to B, but then I add this transaction field, a close remainder to field, and this says that I transfer nothing to B, but then I close the account and I move all the funds therein to another participant C. And so the overall effect is that I've closed the contract and I've transferred to C the whole amount. So the problem is that here I forgot to check that the close remainder to field was not set. So the close remainder to field is something that changes the semantics of the transaction compared to their type. So, and this example is very simple and minimal, but the truth is that in TEAL scripts, you usually need to add a lot of checks to see that certain fields of the transaction are not set and some others are set. And in this way, you understand the actual behavior of the transactions. So, quickly, the contribution is a formal model where all the possible behavior of transactions, no stateless contracts, has been formally specified. And this model has been inferred from the documentation of Algorand, but this was not enough in most cases, so we had to inspect the source code, and in some other cases, we also had to perform experiments. And we have validated this model through experiments. Based upon our model, we managed to prove some basic properties of the Algorand state machine, for instance, that there is no double spending, that the value of asset is preserved except for a specific kind of transactions that destroy assets. And we have also formalized a variety of contracts, and we have proved their security. Just a few insights on our model. We have reorganized the transactions types by their functionality. So for instance, rather than using transaction fields to understand the semantic of the transaction, we create a new transaction type. And in this way, we have defined the semantics of this transaction as a state machine. And rather than using the bytecode language TEAL to specify contracts, we have proposed a new declarative language with the formal semantics. And we have specified a compiler from this declarative language to actual TEAL bytecode. And in this way, the compiler takes care of adding all the needed checks for the transaction fields. This slide just to say that the formal model fits in one slide. And this is an example of a contract specified in the declarative language. You see that in this case, there is not a big difference between the TEAL code and the declarative contract, but in more complex cases, the difference is substantial. And just to mention a few examples of contracts that we have managed to specify. We have specified the Oracle, the hash-time locked contract, and also two-player lotteries, and some DeFi contracts. And the one marked with the green label, it means that we managed to carry a formal proof that they are secure with respect to the specification. And interestingly, we have also managed to model finite state machines as stateless contracts. Of course, it is practical only if the number of states is not big. Okay, I want to skip some slides and jump to the conclusions. To conclude, our formal model abstracts from many low-level details of Algorand, but still it covers most of the features of the stateless machine. You can see our formal model also as an alternative form of documentation with respect to the official one. In the official one, many corner cases are not specified, while in our formal model, you find the behavior of all the corner cases. And this is fundamental to study the security of contracts. As an ongoing work, we are developing a tool to translate the whole formal model to Algorand. But for the moment, this tool just implements the compiler. And an ongoing work is the specification of the stateful contracts and building upon this, the creation of new verification techniques for Algorand contracts. I've finished. Thank you.